Okay, so uh, which of these statements about backpropagation is true, right? So it is used to optimize weights in the network. Um it is used to compute the output of a neural network. It is used to initialize the weights of network. It's used to regularize weights of neural network. Right? So the right answer is, uh, I mean, ideally, it should be to compute the gradient uh, of the weights, uh, gradient of the loss with respect to the parameters, right? So the closest one is it is used to optimize the weights in the neural network. Okay, any questions on this? Okay, we'll go to the second question. Let y be the true class label and p is the predicted probability of the true class label in a binary classification problem. And which of the following is the correct formula for the binary cross entropy loss? Okay, so the correct answer is this second. So let me explain this in a bit more detail. Um, okay, so you have some model and you are given an input x and you are predicting some probability that it belongs to 1 or not. Right? P represents that your output is 1. Because it is binary, then 1 minus P will represent that your output is 0. There's a confidence that your output is 1, your confidence is output is 0. And you know that the ground truth uh, for this x can be either 1, uh, either 1 or 0, right? So the cross entropy loss is given by this thing minus log. In this case, it is this log 1 minus p. So any one of these terms will be active, right? Because y is either 1 or 0. If it is 1, this goes to 0, and if it is 0, this goes to 0. Okay. So, mm, so if you are familiar with something logistic regression, so this is nothing but that logistic regression loss. Any questions on this? No? Yes? Okay, then we can go to second. Right. So this is a multi-class classification problem. So it's the same thing. It is the same as the previous questions, but now you have more than say two classes. So it's multi-class typical cross entropy loss. Right? So which of this is correct? Basically, this is the right answer. So let me explain that more clearly. So here you have to predict either 1 or 0, right? Now in this problem, there is an input x and there is a model, some model. Now you have to predict one of C classes, 1, 2, 3, and so on, C. There is no more predicting a binary class, right? Now you have I mean, more than two categories to choose from, right? Now here the model predicts, say, uh, given an X, right? You train a model, say you have a model and it predicts that X belongs to class 1 with probability 1, belongs to class 2 with probability 2, and so on. Probability C, right? And you have ground truths as well for this Y. Now here the ground truth is a vector, right? Say if class 2 is correct, then there will be 1 in case of the second index and rest will be 0. Right now the cross entropy loss is simply yc log of your PC. C goes from 1 to, say, capital C. Remember here also only one term will be active, right? Depending upon where this y, wherever this one is there. I mean, you have the ground truth, right? That corresponding to this input, you know which output is one. So only that will be active, others will be zero. Right? For this is the case for multi-class. So any questions on this? Okay. So uh, can a cross entropy loss be negative between two probability distribution? Can this loss be negative, the cross entropy loss? Any guesses? You can write in the chat box if there are any guesses. Can a cross entropy loss be negative? Okay, so let me explain. Cross entropy loss cannot be negative. So given any two probability vectors, a discrete probability mass functions P and Q, right? So they belong. This is a vector of say length C, and this is also a vector of say length C. Right? This is defined as negative of say PC log of QC. So sum over 1 to the number of classes, the K classes. Right? So remember, this is a quantity log of QC, right? QC always lies between 0 and 1. Right? In that range, logarithm is negative, and you already have a negative sign. So this is a positive quantity because PC is always positive. The P and Q, they all lie between 0 and 1. Okay, is it clear? Okay. Hmm. So now it's the same. I mean, the question is you are given two probability vectors P and Q. Under what conditions the cross entropy loss will be minimized? You know that cross entropy loss is always positive, right? What is the lowest value that one can get? Right? So this will be minimized when P is equal to Q. Like when two distributions are equal, then it is minimized. Okay, so can go to next question. Which of the following is false about the cross entropy loss between the two probability distribution? It always lies in the range 0 to 1. I mean, this is wrong because your cross entropy loss can go, I mean, it can go to plus infinity. Um, and just now we saw that it cannot be negative, right? And yeah, it can be one, it cannot be one if we don't know about it. And it is always positive, this is true. And this is not true, maybe true, may not be true, the last one. And it can be negative, this is false. It is always in the range 0 to 1, it is false. Okay, so right. So now the question here is so there are some events. So x1, x2, x3, so on, xn are events. This can be thought of if n is 6, you can think of x1 is the event of getting 1, x2 is event of getting 2, right? The phases of die. And what can you say about the entropy of that system? Right, so entropy is always it is greater than or equal to 1 uh, in this, at least in this setting. Right? So let me explain this a bit more detail. Right, we are given with x1, x2, x3, and so on, so xn. Now each of them occurs with probability 1 over n. Now what is, how is entropy defined? It is defined as something like this: minus pi. Sorry, my bad. Now pi is 1 over n, right? So this is minus 1 over n and log of base 2 of 1 over n, right? So this is nothing but we are summing it n times this quantity. So this n will cancel, and what you get is log n base 2. For n greater than or equal to 2, which is the case actually as it is given n greater than 1, this quantity is always greater than 1. Any questions on this? Okay. Yeah. Now we have a problem where we have the data x and labels y, and they are related to this relation y is equal to 1 plus x power 4. So which of the following is not a good choice for activation function in the hidden layer if the activation function at the output is linear? So basically, all you are given is some relationship between the input and output, which is definitely not linear. Y is equal to x power 4 is non-linear. So definitely, you cannot have a linear function in the hidden layer, right? So a linear function composed with linear function, you always get a linear function. Right? You can never match this kind of relationship. What I'll explain this in a bit more detail. Um, so you have given a relation y is equal to 1 plus x power 4, right? And so uh, this x power 4 is non-linear. And now say if you have a network where you take an input x and you have some hidden layer, which is w times x, and say you have some non-linearity sigma applied on this, and final output is say w, say y. All this is w1 and w2. Right? If this is a linear, um, if this is linear, the entire thing will be w2 times sigma of wx. I mean, because it is linear, you say write this as some constant times wx. Right? Now, in the end, what you get is w2 times w times x. This is a linear function of x. Now, this can never approximate your nonlinear function, 1 plus x power 4. Right? So, any other nonlinear activation works, but not this linear thing. Is that clear? If not, I can explain this again. Otherwise, we can go ahead.
Sir, can you please repeat the answer?
From where you have a problem understanding. The question is clear, right?
Sir, concept clear नहीं है.
Okay. Okay, so let me explain the question again. The question is you are given input-output relationship, which is y is equal to x power 4 plus 1. And you are asked a question, which of the following is not a good choice of activation function in the hidden layer if the activation function at the output is linear, right? So here is it. So this is what is given, the map between input and output. And this is how a typical neural network looks like. X is taken as input and you have W times X. And you apply a nonlinearity on this W times X. And because it is already given, my output as a linear function and there's no activation on it. Right? It's a linear activation. Say I assume W2 is my activation. right? So this is how a typical neural network looks like with one hidden layer, which is this. Now, what is output? Y is nothing but W2. This W2 is operated on this sigma times of this WX. Okay. Now, because if your activation is linear, right, which is sigma times WX, I can write this as K times WX. Some K is some linear thing, some constant. Right? If you want to be more precise, you can write this as WX plus B as well, something, which is in this case you call it as affine. But for simplicity, let's put B is equal to 0. I mean, if this is the case, what you have achieved here is Y is equal to some W2 times W times X. And what you wanted is Y is equal to X power 4 plus 1. Right? With a linear activation in the hidden layer, you can never approximate this thing. So this is not a good choice. This is what I'm saying. Okay.
Okay, sir.
Yeah. So here we are given a probability of two events. Now, event A happens with a probability of 0.95 and event B. Following statements are true. Event A has high information, event B has low information, and event A has low information, event B has high information. Right? So here, right, whenever you have the weight is defined, information is defined as negative log probability. So whenever there is lower probability of happening an event, you have high information, right? So event B has high information, event A has low information. Going by that, clear?
Yes, sir.
Okay, let's go to second last question. Which of the following activation can give positive outputs greater than zero? Right? Let's see how they look like. Um, so we are given with uh, sigmoid, right? There is sigmoid. How it looks is this is a zero point 0.5 and this is 1, right? So this is how your sigmoid looks like. And there is ReLU, right? And there is a linear function. So this is a linear function. This is ReLU. So this is linear. And this is sigmoid. And there is tan H. Right? That goes from -1 to 1. And the question is, which of the activations always have positive outputs greater than 0? This is
Sigmoid.
sigmoid, as you can clearly see, right? Yeah, this is the graph completely lies above the y-axis. Okay, so this is all I had for today. If you have any questions, you can ask me. Otherwise, we can end the session. Any questions I can answer? I'll try to answer. Otherwise, we can end the session. No questions?
No, sir.
Okay, so you are guys have done with back propagation. So given any neural network, you should be able to write the back propagation for the weights. Um, well, we'll see. I mean, next week probably I'll try to um, do it for a simple network. Okay, so yeah, let's meet next week. SVM, I don't know. I mean, not discussed, typically not discussed in deep learning class. I mean, it's more of traditional ML topic. I don't know if is it there in the syllabus. We'll discuss. If it's not there, we will not.
In this video, we will go over how backpropagation is computed in a neural network. So to demonstrate this, we will consider a simple two-layer neural network as shown below. So X is the input, and that X is passed through first layer, which is composed of weights W1, and the output of the after applying weights to X, that is W1 times X, we assign a value of Y1, and that Y1 is passed through activation. It is denoted by sigma. This activation can be any of the ReLU, TANH, sigmoid. And the output of activation is denoted by Y2. Y2 is again passed through W2 to obtain finally the logic, what we call as logics in neural network. And this Z is again passed through some deterministic function G. So for the classification layers, this can be a softmax. So as described, X is the input, Y is the ground truth that we are supposed to learn the function to map from X to Y. So y hat is the prediction of the neural network as depicted here. And L of y comma y hat is the loss function capturing the discrepancy between the predicted value y hat and the ground truth values y. So for simplicity, we assume that there are no bias terms in the neural network. So as described, y1 is given by w1 times x, y2 is operated is obtained by operating nonlinearity on y1. This is essential, otherwise this would be a simple linear network if there is no sigma. Again, z is obtained by operating y2 on operating w2 on y2. Finally, we get the predictions by hat by using a deterministic transformation G on Z. Typically, G is, as I said, G is typically softmax for a classification task. And our goal is to compute the gradients using backpropagation algorithm. That is, the gradient of L with respect to W1 is also denoted by 2W1, and gradient of L with respect to W2 is denoted by 2L. And for to make things concrete, we assume X lies, that is the input lies in D-dimensional space, and the matrix W1 lies in D1 cross D space, and W2 matrix lies in D0 cross D1 space. And D0 represents the D output dimension. So Z belongs to R bar D0. So does Y hat. Y hat and Z has similar dimensions. Right. So to compute the gradient of loss with respect to W2, we have to backpropagate. So loss is computed here with respect to Y hat. So gradient first have to come from loss to Y hat, and they have to go from Y hat to Z through G. And again, from Z, the gradients has to pass on to W. So this is what we call as a chain rule, which is given by, this given like this. As we have discussed, the dou L by dou W2 is the gradient of loss with respect to Y hat. Again, how Y hat is obtained through from Z using G. So that Y hat, gradient of Y hat with respect to Z, finally gradient of Z with respect to W2 is what, by doing this three steps in one go, we obtain the gradient of L with respect to W. So for simplicity, we denote dou L by dou Y hat gradient of L with respect to 1. Remember, the dimension of Y hat is D0, as Y hat is obtained from Z, and Z and Y hat have these similar dimensions. And finally, dou Y hat by dou Z is nothing but the gradient of G with respect to Z, but G can be softmax or any other function, depending upon the application, whether we use regression, classification. Really, classification tasks typically have softmax. So finally, we obtain the gradient of loss with respect to the parameters W2 as the element-wise product of gradient of loss with respect to Y hat and G prime of Z. G prime of Z is nothing but the active, the softmax derivative. If we are doing the classification task. And finally, this is obtained by, so till this point, this is gradient of L with respect to Z, and gradient of Z with respect to W2 is given by this Y2 transpose. So if we to check the correctness, we always have to check the dimensions of W2 and dimensions of gradient of loss with respect to W2. They both should lie in the same dimensional space. If you remember, this is an element-wise product, and gradient of L with respect to y hat lies in D0 space, and gradient of G with respect to Z also lies in D0 space. So their element-wise product also lies in D0 space, and that is um, outer, that is by its structure, we end up doing the outer product with Y2, and Y2 is D1 cross 1, and so this is D0 cross 1 and this is 1 cross D1. Finally, we end up getting D1 by W2 in the space of D0 cross D1, which is same as the dimension of W2. So that's how we compute the gradient of loss with respect to the parameters W2. And so we need to compute the gradient of loss with respect to W1 as well. So if we see the computation, we have backpropagated from loss to y hat to z, and z to w. But now we to compute w1, we need to backpropagate from z to y2, y2 to y1, y1 to w1. So that is the reason we need a gradient of loss with respect to y2, and that is given by gradient of loss with respect to z and unit of z with respect to y2. So gradient of L with respect to Z we have already computed here, which is this part. There's nothing but gradient of loss with respect to y hat, and again the derivative of y hat with respect to Z. So finally, we get the gradient of loss with respect to y2 as W2 transpose dual by 2Z. And y2 is in the dimension of r power t1. So does dual by dy2 has to be. And W2 dimension is D1, D0 cross D1. W2 transpose is D1 cross D0. As we have already discussed that dual by dou Z always lies in the D0 dimension. And hence, dual by dou y2 lies in D1, R by D1 cross. So finally, we got dual by dou y2. But to get to W1, we need to pass through y1. So hence we need dual by dou y1 as well. But y2 and y1 are related by very simple relationship through activation function. Right, so that's why dual by dou y1 is nothing but the activation function times dual by dou y2. Activate when gradient is passed through activation function, the dimensions are not changed, and it is an element-wise operation because each element activation function is applied in an element-wise fashion to a vector. And so it takes a different forms when the activation functions are different. For relu, it is different. For sigmoid, it is different. For Banach, it is different. And so finally, after we obtain dual by dou y1, we get dual by dou w1 as dual by dou y1 times dou y1 by dou w1. So dou y1 dou w1 is in this context it taking up the form x transpose. So remember that dual by dou y1 has a dimension d1. So dual by dou y1 as y1 also has dimension d1. And so this is d1 cross 1. And x is the input that is lies in the dimensions of d. So x transpose lies in the dimension of 1 cross d. So this is d1 cross 1 and this is 1 cross d. And we obtain T1 cross D as W1, 12 by 2 W1 length. The W1 also lies in the space of D1 cross D. Remember, this is done for single sample X. So in general, when we are evaluating the neural networks, this we are supposed to average across many input samples before taking a gradient update. So, so this is how we perform backpropagation in a neural network. So this is demonstrated by taking a simple two-layer neural network, but this holds the method holds in general for any number of layers.